Okay, so good morning. Today we start early, so we can do many things. So you remember where we stopped yesterday? So we were looking at this pion form factor. Okay. For the coupling of the pion to the vector current. So we define this form factor. And what we have seen that okay, in KPT we have an expression which is of this form here. We have this 2L9 divided by sorry, take the precise result. Yeah. And the loops are very small. Okay. Maybe one should put it like this. Actually, this is what somehow define the pion radius. And I was telling you this term is much bigger than that one. And it's really well approximated by something like this, where this is the mass of the rho. And of course, this is a well-defined, this is a physical quantity, okay? It's the pion radius, while the counter contribution by itself is scale dependent, the loop contribution itself is scale dependent, but the sum is a finite measurable quantity. It's really the slope of this form factor that you measure in experiment. And this is not a chance. Indeed, actually, what experimentalists have done experiment also at higher energy, and it's really a good approximation of this form factor as the following structure if we go to even higher Q square. So let me now, in all the rest of the lecture, I will call MV the mass of the rho and all the octet of resonances. Actually, the form factor turned out to have this type of form, to a very good approximation, what people call vector meson dominance, which, again, if you expand it now, you see this, if you expand it, becomes 1 plus Q square over MV square plus Q square over MV square, and so on. This is something that will appear at higher order in the Chiral expansion. This is this first term here. Again, this structure is not surprising. Well, it's certainly with respect to this form here, this form here, we say that has a bad behavior at high Q square. So I think this is Q is the momentum transfer here, or the way we define it yesterday is the momentum transfer of the current to the pions. So you immediately understand that if this grows with Q square continues forever, for instance, if you do it plus and minus to pi pi, this cross section would blow up. So clearly cannot hold. Okay, while this is much better, goes like 1 over Q square. So it's a nice behavior at high energies, and this behavior is ensured, if you want, by the contribution of this resonance. So the contribution of the resonance, the one is fixed by if on the electric charge, the fact that you have a slope, I mean, is consistent with the Chiral expansion, but then you see that the high energy behavior, on the other hand, seems to be controlled by the resonance. So what I want to discuss next is indeed a more general, trying to exploit this fact a bit more generally. So it looks like, and especially in all the cases, this is why I put there my table with the Li. In all the cases where we have big Lis, big counter term at order p to the fourth, especially all cases 1, 2, 3, 9, and 10. These are all counter term related to derivative operators, okay, which do not contain quark masses, contains either derivative of the U or coupling to the external field. And here we can have contribution by exchange of resonances, of vector resonances. And it's very interesting to show that actually all these things get basically determined to a good accuracy by the contribution of the resonance. And this is something that, if you go back to the other side, this is something that goes well with the large NC arguments. You see what happens, what we seem to see here is that this form factor, okay, so we have our pion. Let's now do the pion as, okay, in KPT we have just the point-like interaction, okay? And what this behavior is saying is, look, actually, the interaction at the end is mediated. They form a resonance, okay? So this is my vector resonance. So the two pions form the resonance, and this is what is really coupled to the current V. Okay, so this is. Okay, and this is what you would expect in. So this is a contribution which is not suppressed by large N, while the pion loop, okay, the pion loop requires something like this. I have to create a. So this is just by QCD argument. This diagram here where I create two pions. This is 1/C suppressed with respect to this one, okay? Because simply it's just a counting of the color, the arrangement here to produce a loop, okay? You don't pay any suppression to produce gluons, but to produce a loop, you have to have the two gluons to have the same color if you want to match, and this is why it's 1/C suppressed. Well, this is not 1/C. So here are all the gluons, okay, and there is no suppression. So the statement is that whenever, and so what we are saying here is that whenever you have something like this, that we can have a contribution of a resonance, okay, this in the limit where the mass of the resonance goes to infinity will shrink to a point-like interaction. That is what we identify with the Li. Okay. Now, of course, an objection here is, well, the Li are scale dependent, while this is something which, on the other hand, if I compute it like this, will not be scale dependent. So how this comes? Well, if you look here, and now we have the values there, and we also have the anomalous dimension, which we didn't put there. The anomalous dimension of this, we call it the beta function of L9 is such that actually if you look at L9 and you vary between 500, so the K on mass up to 1 GeV, which is the reasonable range where you expect this theory, it varies 10% with respect to its central value. And this is indeed consistent with the fact that this loop is small. Actually, of course, the loop correction are there, but this really is a 10% contribution of this leading effect, which is this one here. Okay. And again, this is something that we can understand by large NC argument. And now, what I want to discuss next is how to do this in a bit more systematized way. And the way to do that is to introduce the resonances in our Chiral Lagrangian, which again is also an interesting exercise, how to couple our pions. So what I want to do is to really look at all possible interaction of pion and external field with an octet of vector mesons, axial and vector, integrate them out. So I mean, consider this limit where it will lead to a point-like interaction, then derive the expression for the Li. Okay. So now I do something this one should be worried how we introduce these resonances, which actually are heavy state. So I introduce them in my Chiral Lagrangian, but then I really, they are not truly external state. I will treat them as dynamical, but I will only treat them as dynamical for this 3-level contribution, okay? Just to determine this, I will not put them inside loops. Okay? And this is then, it's a consistent procedure. Actually, toward the end of the lecture, I will also put them in the loops, but okay, let's start from the basic thing. So this is the formalism I want to discuss now. So how to add, so if you want, is a semi-dynamical treatment of the inclusion of resonances. So how to do that? Again, it is really exactly like what was discussed by David Kaplan about the inclusion of baryons. So the only thing I know about the resonances is their transformation property under my unbroken subgroup. So remember, G is my chiral group. Now I stick to 3 flavor. My unbroken subgroup is, on the other hand, this one. And I know how the resonance transform. In particular, I'm interested to include here an octet of resonance. So, you know, the vector resonances, the rho and the k star and the omega and the phi form an octet plus a singlet. So the octet, as you say, if I have generic field R, this is the field of the resonance, will transform as an octet. We transform like this, right? And then I think now you know how to do it when we have something like this. Well, then I have to build my ingredients with the CCWZ formulas. So I know how to do derivative here. So for instance, when I want to act with the derivative on this field, because this, this is a transformation under H and the transformation under G is this, right? Now this, you learn. Again, the difference between these two, let me stress it once more. So this is a linear realization. So we understood why this is linear. This is, okay, this is obviously linear in R, okay? Also, this one is linear in R, but it's not linear in the Goston boson, which are sitting there. So here, there is a dependence on the field. So this, I always write it like this, but in practice, it would have been better to write it like this. So the dependence on phi is non-linear, okay? So they depend on the field in a non-linear because it's an exponential, so it's non-linear. Okay. So when I want to do a derivative, here I have to introduce my, this we have seen it last time. I introduced this gamma mu, which I think I realized I could have had a sign mistake last time, but I think this is now, I checked it, this is now correct. This I built with my little u. Okay, so I hope if you did your exercise, you should have checked that this transform as okay, so it's exactly what I need to put here to compensate when the derivative act on R. So this becomes invariant, okay? Again, this is what David Kaplan was calling V mu, remember? Okay. I call it gamma mu. So these are ingredients. Now, now this is generic. Maybe I can put the other ingredient, the other very important ingredient that we need to put is what we were calling A mu, you remember? So which is something that now, let me now call it, sorry, I changed once more notation. I stick to the original notation of Ecker and company, which actually yesterday we have seen it in a different form, which is just it's nothing but like this. To understand why these two things are the same. So let's do it as a morning exercise, okay? To show, so these things I can also write it like this thing. Let's check. First of all, let's see the transformation property. Okay, the transformation property of this object. Remember that this goes into G left, U dagger, H, but actually what I will be interested here is more this transformation property, G right dagger. So when I put it here, why my big U goes into G right, big U, G left dagger. So you see clearly that if I put this transformation property here, I will get that this goes into H itself. Okay. Here there is a G left. So in this case, I use this transformation property, and I get this. Right. So this U mu is something that transforms exactly like our octet. Okay, so it forms an octet of axial type current. So we'll start with the first term. So here I miss. This starts with the mu pi. So it contains the pion field, okay, at the lowest order. While this other term, this is different, right? This actually also transforms like this, but has this other piece, okay, which is important, and starts with 2 pions. So this is a vectorial type thing. And I promise, okay, finally I want to show that we can also write it like this. See, again here, these things. So if you want to play with Chiral Lagrangian, you should always do these games of putting sometimes U dagger U. So you see here, let me put a big U dagger, G mu U, little u. Sorry, this is just one. Okay. Now the other trick we can always do is now I take this term here, I can move the derivative here and change sign. So this will become minus I U dagger, the big U, the derivative now acting on U dagger, the big U, and the little u. And now this is just U square, this is U square. So here, this little U dagger annihilate one of the two, so this becomes my, which is the other expression, okay? Just algebra, not in too deep. Okay. Okay, so actually, yeah, this was just for as a warm-up. So really, these are my ingredients. Now, finally, I should tell you, okay, what this is generic for the resonance. Now, when you want to describe now we want to describe a vector field, okay, the rho, or the A1, so the axial vector. Now we need to know that to put a vector field, you say, okay, I will put something instead of this R, I will put some R with an index mu, which is, of course, is the natural way to introduce a vector field, but it's not the only way. And actually, this is dangerous because actually, if you just put the formulation in terms of the field with Lorentz index is it's not optimal for a massive vector field. Okay, then you could use the Proca-Lagrangian, but this is problem. And also with the power cantic of the Chiral expansion doesn't really fit well. The nice what was shown by Ecker et al. That there is another formulation which is much more appropriate for doing what we want to do, that use a tensor to describe our vectors. If I take an antisymmetric tensor has only 3 component, symmetric, real antisymmetric tensor, which is exactly what we need. So I will introduce my 2 tensor, V nu and A nu, which transform exactly like them. So generically, sometimes I call them R mu, but V mu will transform as H, and similarly for A. Okay, and maybe yeah. Let's first look at the Lagrangian for this field. First, the kinetic term of the Lagrangian. Now the kinetic term, I do it with derivative acting on this guy, collectively I call them R mu. So I have these things both for V and for A. And then I have to put the interaction term. So that is the Lagrangians. You have two derivative and the mass term. Very nice. And then now for the interaction, I need to distinguish the vector in the axial case. Maybe this I should write it. So it stands for sum of R can be V or A. What the interaction term? Now I have the following term. Now the last things which I didn't, so here you see everything you know, this U mu. So this term, for instance, is easy, right? So you understand, because this V transform as this, that object we know that transform as H. So this is clearly invariant, right? What are these guys? Well, these guys are terms which contains our external field. Okay, so will be U this is sometimes I call them L mu nu. So these are really the external field, okay? You see this by construction transform as okay, so these are basically I take my external field L and R, I sandwich them with U or U dagger such that then they transform all of them homogeneously under this H group, like an octet. Now this F transform as an octet, U mu transform as an octet, everything, so it's just, then it's trivial, I have just to take traces. And then the only difference here that V mu I couple to the one with the plus, which is the left plus right because of parity, while A I will couple to minus because of parity. Okay, so these are the only thing where I put the fact that this is a vector resonance, this is an axial resonance. Similarly, also here the vector resonance, because this interaction I want them to preserve parity because it's a strong interaction. So the vector interact with pions. So this GV, the GV is what control vector to pions. FV is what control vector to photon, and FA is what control, well, that is axial, so this is the vector, axial to pion photon, for instance. Sorry, minus, well, most control the coupling of the axial current to the external axial. Or this could also be, yeah, this is just the axial current, okay? Of course, this will control also vector to, I can also include more pions, okay? Because when I expand this, there will be more pions. So as usual in the Chiral Lagrangian, this is this plus any other terms with more pions. When I went?
When you went to, instead of using mu, you started writing it.
Oh, that's a good question. I have not yet fully told you why. You're right. So why I did that? But then there is another question. But let's so why I did that? Well, the first clear advantage is that now you see that these interactions are always of order p squared with the external state. So here is my resonance. This is something which is of order p squared because it's these terms here which contains L mu nu, which is of order p squared. Also, this is here is of order p squared. So this is really nicely built in, such that then when I will contract two of them, I get p to the fourth. And actually, it was for shown that this way is the most general that you get all the P to the fourth that you can get, okay, without any assumption, with all the possible maximal number of free parameters. If you use the V mu, okay, you are more constrained. So something appear at order even P squared, renormalize the P squared, something order happen at higher order. Because so there is a mismatch with the counting, which is not a problem, but this means that then you will need to add other contact term and becomes more messy. This was a very nice discussion at that time when this was, at the beginning people strived with the VMU. For instance, you know, these hidden gauge formally started, but then it's more constrained. So then you have some built-in relation. Well, this is the most general. So I have the most general coupling for the V2 pi pi, the most general coupling for the V2 photon, and the most general coupling of the A2 photon. All the rest is fixed by chiral symmetry, okay? But these three, for the moment, they are completely independent, okay? Which is, so I'm not putting any extra ingredient because I've chosen the formulation that allow me to write all the interaction of order P square. You have a question? Yes, that's, of course, that also I've not shown it, and I show you. So first of all, what is this V mu? First of all, what is this V mu is something that, so this will be a matrix like as usual, okay? It's slightly like so this we call it the K star, and there is the K star 0. Here I have the K star minus, and here I have the anti-K star 0. Yeah, let me put it like this. There is something missing here on the diagonal. Plus, there are the term coming from the omega and the phi, which I've not put because it's a bit tricky because here I have to subtract the singlet. And okay, it's a bit of a long story. I don't want to enter. Maybe we can discuss in the as you probably know, the point that the omega is really the singlet here on isospin, but there's no component here. While the phi is mainly an SS bar state, so it's only here. So which means that there has to be a superposition. Actually, well, I can tell you, so there has to be a superposition that we can call the omega 8, which is a superposition of omega and phi. That so the omega 8, the octet one will have coefficient 1 over square root of 6, 1 over square root of 6 minus, sorry, and minus. Okay, but then there is also a singlet. But the singlet we're not interested because the singlet in the trace will go away. Okay. So because the point that here SU3 breaking somehow split the octet and the singlet and into different mass state. But again, this mass splitting is not big, this is just related to the strange mass. Okay. Finally, so this is V mu, of course, this is as in all of these have index mu nu. Okay. Finally, yeah, the key equation, which of course you want to have is what is the single particle state. So how these act on my vector state of momentum and polarization. And this is by construction, of course, we take it as a definition. This is has to be antisymmetric. So this is how it acts. So you see here, for instance, if I take P mu, okay, if I act with the on my vector state, then P mu will P mu epsilon mu is 0 because still this state satisfies. So for a non-shell vector, what I get is just here I get m square epsilon mu. Okay, so this is what somehow is what you would probably think is the usual V nu, the vector formulation, okay? But that's true on shell. Yeah. Yeah, sure.
The row has one mu index.
All of them have, so all of them have two index, right? So all of them have two index. No.
That's not okay.
No, so here there is no derivative, okay? Simply is a tensor with two index antisymmetrics, which, so this is the key, this is, I should put it with, so this is the key declaration, okay? That when I have a vector, I can define a field such that acting on the vector give me that as a single particle state, okay? Indeed, the connection between the two formulations on shell is just given by that. If you want, you can think as V mu as the derivative on that, but on shell, this is why P caps an M square here. Sorry? Yeah, epsilon is the polarization of the Ramanujan, which the force defined it's spin. Okay, the three polarization. Indeed, there is only this condition is fixed. So there are the two longitudinal, so the two transverse and one longitudinal polarization, as you expect from. So a generic massive vector, which doesn't need to be. See, this is, we don't want this to be gauge vectors. So the vector formulation is really good. It's necessary if you want to have a gauge vector associated to the gauge transformation. Here, this one, we don't want to be a gauge vector. We want to be an object, okay, the most general object that describe a state with three polarization. Okay. In SU3 space, transform like this. No, yeah, because, so sorry. Okay, if you don't want to see the zero, then I have to put the, okay. I have to put the omega 8. So that then I have to put omega 8. Yeah, maybe it's better do like this. So here there was the, sorry, this is, yeah, but this is too long. This is why I didn't want to put it, but. So this is the first entry is there. Then here there is rho plus, so the second entry is this rho 0 over square root, all this square root. So this is minus. And here there is the, K star plus, here there is the K star 0, and here there is minus 2 square root of 6 omega 8. So I call omega 8 the component of the octet, which is the singlet under isospin. Okay, and I told you this omega 8 is a mixture of the physical state, which are omega and phi. Okay, that is because they mix with the singlet. Okay. Are there questions so far? And also this is, I think it's a nice way also to see, yeah, really the power of the Chiral Lagrangian when we want to go beyond to couple it to other things again. If you want to go to heavy hadron Chiral perturbation theory, you have to do the similar type of game, although your field will have a different transformation property, but always the game is always like this. Okay, you define the transformation property of whatever you want under H. This is the only thing you know from nature, okay? And then you couple in all the possible way using essentially these are the two big tools, the connection and this term which transforms the axial current, okay? Sorry? This is a free parameter, okay? It's a free parameter, and you see this is a free parameter I could have put it out of, well, in the limit of no SU3 breaking, this is just a constant. I could even put SU3 breaking if I want, okay? But it's a free parameter. So indeed, good question. How many free parameters we have? So a priori, at this point, we have 5 free parameters. So we have MV, MA, and then we have FV, how we call it, FA, and GV. Okay. So indeed, at this point, you say, well, basically, I have five parameters. I want to fit. You will see this will contribute to this 3 + 2, 5 coupling. So there basically will be 1-to-1. Okay. However, then what I will show is that we can put extra constraints dictated by QCD that will reduce all of this just to one parameter. That is again, somehow using Lagrangian argument, good high Q-square behavior. That is nice. So we really, what happens is the beauty of QCD and Lagrangian and this vector correlation function. Really, this vector state seems to provide the best interpolation between the KPT, which really embed the property at low energies and this derivative expansion, with perturbated QCD, which on the other hand has a completely different behavior in terms of correlation functions. Everything goes like 1/Q², and so like you see there in the vector form factor. So adding the pion itself cannot do that, can never give you terms that go like 1/Q². And so while the vector resonance really with special choice, which actually turned out to be the correct choice also in experiment, provide a very good interpolation. Okay, but that's what I want to discuss next. Yeah. Yeah.
The right-hand side, you want decay constant, not this.
So this is the decay constant. So that's what I say. So this FV, so how this is a free parameter. Here. No. This is here. There is no FV because this is really the action of the field on the state. Okay, so this mu is really the raw field. So this is how my raw field annihilate. Okay, is how it acts in terms of operation of creation and destruction on the single particle state. So here there is no FV. Okay, there is no decay constant. This is just only the mass, because it really this only depends on the. So this is just related to the free Lagrangian. Okay, then I want to treat the coupling. This one, the coupling of this state with the photon. This is a free parameter, and this will be my FV. Okay. So, and actually, again, thanks for the question. Let's look at you see the way I define all these parameters. All these are dimensional parameters. Okay, they also have dimension of mass. You see here from the counting. Basically, this term here, the way it is defined, count as a dimension 1 field. Okay, as we usually do. So this is a dimension 1 field. So this tensor here, this has dimension 2. So this is dimensional. While here, indeed, my Lagrangian has a dimension 1 field. There are 2 derivatives, so the power counting is as usual. Okay. Okay. Good. So, okay. Now finally we put all these things, we can integrate them out. Okay. We put.
Yeah. It doesn't capture any interaction between V and E.
Yeah. By construction, there is no interaction between. I could put it, but this will contribute only to higher order terms. So I could put it, of course. I could put all of them, but this is the only thing I'm really also what I want to do is just what I sketched there. So I just want to have interaction between pion and the external field and cross them together. If we will have 2 interactions, then will something we have 2 inverse mass, the propagator will be higher order. Okay. One last thing I realized. So what I didn't give you is, but this you could derive it from this Lagrangian here is of course the propagator. Okay, the propagator is important, and it is not standard. So from this Lagrangian, you invert this quadratic term, and you get the propagator. Okay, let's look at the propagator. Okay, that's it. And yeah, it's a bit weird, but at the end, it's not that weird if you think a bit. So there is a contact term. This is important. And then there are terms which goes like Q mu, Q nu. So actually this, really for what it matters, this is G mu. Oh, sorry. Okay, so the leading term, which is when this will cancel, is just a contact term, okay? Which is very nice because it's telling us that basically when I want to contract these two terms, I will simply have this times that, and I just get my e to the fourth interaction. Okay. Okay, this is a nice exercise. Really, if you have, it doesn't take too long. Take this Lagrangian, it's a quadratic Lagrangian. Do the green function, invert it, and you get your propagator. Okay, it's a non-standard QFT, so I think it's good to do it. That's what you get. But really, see, it's very simple. This becomes a contact term. So finally, with that, it's really easy to get our coupling, okay, the P to the 6 coupling, which I'm not even sure if I put them in, but for instance, well, we can see immediately, for instance, what we get from this and that, okay? Let me put it here at this point, maybe. Sorry? It's, no, it's quadratic, just quadratic, of course. And actually, or maybe I should have, yeah. Actually, and this is m to the fourth, so this is m squared, but this is higher order than in m. Sorry, I put it. You understand? So it's 2 power of q. So you see, for instance, if I contract these two terms, okay, the operator I get, basically I have a contraction between this and that will give me a contact term. So I will generate from these two terms, I will get FV GV divided by 8, and then from the propagator I will get some MV squared, and then we'll get trace of U nu F, I call it F mu nu plus. Okay, that is what I get. And that is nothing but our L9. Of this, if you rewrite it, that's exactly our L9. Okay, easy exercise to do. So this really, so this will be our contribution to L9. And now you see this, they will depend on FG, GV, and V squared. Now if you do all the factor of 2 correct, which I'm not sure if I put it, what you will get is that, and now if you compute your ion form factor, you will get the one that is there is not coming from this term, and you get FV, GV, here you have to stack 2 pions, so you will get F pi squared, and you get Q squared, okay, from this term here. But now, this is really the contact term which I get from this term here. If, on the other hand, I really keep, so this is really, I computed this diagram exactly as I showed there. So here there is GV, here there is the vector resonance. So when I shrink this to a delta function, I get this. But then if I take the full propagator, not surprisingly, I get something like this. Okay, I get the full propagator of my resonance. And now you see that what is interesting, actually, this is not yet, okay, exactly what we see. So this is, sorry, this was GV. This is generic. For a moment, this indeed, still this Lagrangian doesn't know anything about QCD, only knows about Chiral symmetry, okay? And it gives me the most general correction that I can have, which is something that grows with Q square. But actually tell me, look, however, if this is given by the resonance, well, at high Q square, not really goes like Q square, goes like that. Now, if I really want this to go like 1 over Q square, and this is my QCD input, then I get the relation between FVGV and F pi square. So you see this is the power. Then QCD tell me QCD implies that this FV should go like 1 Q square, 1 Q square goes to infinity, and therefore implies that FV GV has to be equal. So this is what we call one of these thumb rules. And amazing, the measured value, this FVGV, you measure it, okay? Because the rho to pi pi coupling or the rho to E plus E minus coupling, you measure it, and they satisfy very well this relation. That's what I was saying, that the exchange, so while the behavior given only by IPT really is a bad behavior at high Q square, when you put the simple this vector resonance, you have all the ingredients to match what QCD tells you at high energy. Of course, this is just the leading contribution. Then there are the Chiral logs, but all these are small effects. The leading thing is really driven by the exchange of the resonance. Okay? And whenever the resonance, whenever this vector resonance, whenever the vector resonance can contribute, they seem to do exactly this job for this basic green function. Okay, indeed, if what I want to discuss, yes? No, there is Q squared, because now this, you see, if this is equal to 1, okay, then I sum and I get here like this. So you see, a priori it could be like that, but only, okay, if I satisfy this relation, yeah, sorry, because I should have stressed it. So only if this is really 1, then this becomes like that. So then it becomes like 1 over Q square. Okay. Thanks for asking me. Okay, so really I see that only for a specific value. And again, you see this with this tensor formalism, indeed, I don't have automatically the good Q square behavior. Actually, I have the potentially the worst one, but then I have all the freedom, and so it's nice to then to check. And this really, it's then you see the constraints put by the Q square requirement. And indeed, as a last thing to do before the break. Sorry, I'm getting a bit lost with my notes. So I told you there are 5 this parameter. Okay, basically there are 4 relations of. So this we find one relation, one nice relation. FV GV equal F pi. So once we buy, then basically we can remove GV in favor of FE and F pi. Okay, and there are other relations of this type. One of the most interesting one, which I want to show, is the one coming from the maybe I do it again here. Maybe let's do it here. So coming from looking at this object here, we had a discussion yesterday at the end of the lecture about L mu, L mu. Now I look at L mu, R mu, okay? So a coupling between an external left-handed current and an external right-handed current. Actually, what I'm interested in is this correlation function in QCD, okay? What I'm really interested is, indeed, I look at here because here I want to compute this in QCD, and so I put the left-handed current here. The left-handed current, when I do my function, I will bring down these things here. And then I want to see what happens with the right-handed current here. You have to mesh the flavor index. Yeah, maybe put new. Okay, so you see, yeah.
The fact that you get only one key, I mean, even if it's something much smaller to the higher spin,
Yes, yes. And I think this is still one of the big mysteries, why the first resonance saturates the sum. So first, now I'll do it with the sum of resonance, okay, for this other case. So here I do it a bit heuristic. Now I'll do it with yeah. Yeah, indeed there are, but they are very, there are some wiggles, but they are very small. So here is something that works really at the level of 10%. So then there are the Panion loops and the subleading resonances, but they are all small. Seems that the bulk of the effect seems to be controlled by that. Indeed, this is not perfect. I'm not doing exact. So yeah, everything, the formula is exact, but then this extra input that we get from QCD, of course, we are some approximate relation, which however are very powerful and give us, I think, a deep understanding of the leading effect in these effective theories. So I think having, more general, having guiding principle when we have these effective theories, now you can think of other effective theories with many more parameters. Having guiding principle, which are the leading effects, it's important. So that is why I'm telling you. So having an idea of what comes in the UV is useful. And of course, you have to do it consistently. So, okay, let's finally go to this thing. So this is, you see, it's I want to look at the correlator between this object here. So actually, I will define my phi left, right. So it's the Fourier transform of this object here, okay? And here, simply by gauge invariance, you understand that this object here has the usual transfer structure. And so I can define a scalar quantity pi left, right, q square, where I simply remove these things. So this structure here is because you know that these things has to satisfy the word identity, right? And again, something that you can try to compute in QCD. Now, why this is interesting? Now we are in QCD in the chiral limit, okay? No masses. Only, and I put here only my light quarks. So what should I get? I think we maybe briefly discussed it. So this clearly in QCD, in perturbation theory, it's always 0. Because here I have my left-handed current. And here I have a right-handed current. So how can left go to right? I need to break current symmetry, right? So how this happens? Well, this can only happen because at some point I will couple with my QQ bar condensate. So there is chiral symmetry breaking. Okay? So we know that chiral symmetry is broken, but in a non-perturbative way. So it's something, if you do in perturbation theory, you always get 0. Okay? No matter what. But we know that at the end, there is a ground state here around where Q bar is non-zero, Q bar Q. So when you couple to this ground state, you get non-zero, okay? So it's really truly non-perturbative things, okay? But again, this is a suppressed thing. So if you try to compute this, that now Q, well, I hope it's clear that Q is, well, you see it here, is the momentum transfer here. So then you can compute in perturbation theory at IQ square, okay? And what one can prove in QCD, when Q square goes to infinity, this pi left, right, Q square goes like the condensate divided by Q to the 6, sorry, the condensate square. So it's really suppressed at high Q square. As usual, as all correlation functions, they tend to be suppressed. There's a nice theory, nice perturbative theory QCD, okay? Now, what happens when we put our resonances? Oh, sorry for this messy use of the blackboard, okay, sorry. So then I can compute that. So we have seen the behavior we have seen, okay, at least I hope you trust me on the behavior at IQ square, which comes from so this is the IQ square behavior. Okay, from QCD. Now let's look at the low Q square. Of course, I can compute that using my nice Chiral Lagrangian. What I get? Well, from my Chiral Lagrangian, I can compute this object. It's just again, I take my functional, I have L, right, I differentiate what I will get. Well, you can do it even diagrammatically. The first term, as we discussed yesterday, is just this, okay? Is the simple pion exchange, okay? Indeed, when you put the pion exchange, you compute, and then actually you remove the term there, then you get simply, yeah. Of course, if I put masses, I will get something, yeah? I think if you put this, with the point that you have to put two masses, okay, one is not enough. If you put two masses, then you will have something that goes like ms squared, and I think probably go like ms squared divided by q squared to the fourth. Q squared to the fourth in the full thing, yes, but of course that you have it. Yeah, thanks. Of course, work masses. So if you want really to go beyond, so want to introduce the breaking theory, you can also do this game, right? But coming to the pure Chiral limit, what I get here is that I get, and then of course we have the counter term from the Chiral Lagrangian. Now I'm looking just at the 3-level contribution. So you get this term here, and then you get L10, which is one of our contact term, which indeed is the contact term between left and right. That is what you get from the Chiral Lagrangian. Okay? Again, completely different behavior, actually, which become worse at higher order. But that's exactly what we had also for the pion form factor. You get something that grows with Q squared because of the momentum expansion, right? On the other hand, finally, we can do it. So this is what you get. Finally, we can compute this using this Lagrangian here, okay? And let me give you, instead of putting only one resonance, now let me put a tower resonance, but all defined in the same way. So what I get here is this result. Hope you actually put minus pi square, so I get, this becomes, so this was f pi square. So that's exactly the same term here, and then I multiply by minus q square, so I remove this term here, and then well, here I'm going in the Euclidean, okay? So this is q squared, it's negative, this is, sorry, but. maybe I should put it like this. Better. Okay, here I don't give you the full conversion, but you see it's very simple to understand. So clearly the resonance will do something like that. Okay, so here there will be my resonance V or A, that both V and A coupled to L and R by construction, right? So it's very simple. Really just by this term, okay? Here you get both L and R. So you either here or here. You have the only thing that there is a minus sign. Actually, this minus sign is responsible here for this difference. In the case of the vector, in the case of the axial, you get the same sign of the pion, or in the case of the vector, you get a different sign. Okay? You buy it? Okay, easy to check it. And now you see, this is what gives rise to the famous 2 Weinberg sum rule. So now if we want this expression to match, so here you have, again, a bad behavior, a very bad behavior, okay, already with something that goes with Q squared here, which is telling us, well, actually at high Q squared, sorry, this goes like a constant. So this goes like a constant, so you get the first sum rule, which is telling us that F pi squared plus sum over A F A squared has to be equal to sum over V F V squared. This kills the constant term. Okay? You see, because when Q squared is large, I can neglect the mass, and I simply get constant. So this was, sorry. These FV are defined like that. Okay? But you can even do more. You can even kill the 1 over Q squared term. Now putting another sum rule, which is this is the 1 over Q squared. You see, because then if these terms, well, you see that that is once you have implemented the first sum rule, then it goes like 1 over Q squared, and the coefficient of 1 over Q squared comes from here. Okay, it should be easy to check. Okay. Of course, I could even, well, now the point is how much we want to go along. Actually, if we have only 2 resonance, V and A, basically this, you can saturate these things. If you just took 1 V and 1 A, you can satisfy both these sum rules. Right? And amazingly enough, the measured value of FV, FA, and the masses really fulfill well these sum rules. So these are called Weinberg. And they really, it's a nice, again, they involve F pi. So you see, it's a really nice way to extrapolate from the chiral limit to the QCD. Okay, so you really say if basically what allows me to interpolate between the, of course I'm not yet there because actually this is even more suppressed. So clearly then something else will happen, but the leading effect, okay, you have to kill the very bad behavior, okay, and this is done as soon as possible by the first resonance that enter in that channel, which are these vector resonances. Okay. So how to derive this one? So these, okay. here.
Left hand side, left hand side.
Or this one.
Yeah.
Oh, this one, would this behave as 1 over q to the 4th? Okay, this behaves, again, if you neglect quark masses. If you neglect quark masses, behaves as 1 q to the 4th. So this term kills me the constant, and this kills the 1 over q squared, which cannot be there at I q squared. Yeah? Yes. Okay, sorry. Okay, so maybe it's a good point to stop here. Okay. And then we continue, and then what I want to show you just after the break is finally, okay, to conclude these things, then we go back to the pion mass difference via electromagnetic effect, and then you will see that if we use these things, we get really a sharp prediction, which is spot on the measured value, which again is nice cross check of all these formulas works. Okay. Yeah, so you see here that indeed L10 basically is just indeed if I take the log square behavior, here I get the log square behavior, it's f pi squared plus, and just do one resonance, okay? So this will be fa squared divided by ma squared. Yep, like this, plus. Now, okay, I did these things here. So if I want to match with that, I have to divide by q squared. I also have to put the minus sign. So this is L10. That's exactly L10. Okay. For L10. The L10, maybe just give me you ask me this. Sorry, can I take one more minute? Just so indeed, finally, indeed, if I impose all this relation, basically there is so here there was this fg equal that, then these two relations, basically there is another one which okay, I don't derive, but finally you can eliminate all the things except MV, okay? That remain as a free parameter. Because I can tell you what happens is that FV turn out to be equal to square root f pi, GV turn out to be equal to f pi over square root, and so on. And really they're all fixed, okay? And finally you can, okay, then you use that and compute this Li with these things that you have done. For instance, L10, you have this relation here, but now you see that these things, then all of them are fixed thanks to this relation except for MV, okay? So what I get is this. So first of all, I define x, okay, to be f pi divided by 2 mv squared. So all of them can be expressed in terms of this only free parameter, okay? Now, this I fix it from L9, which is the one I know better, okay? And then I could even fix it from the mass of the row, but okay? Then if I put the number here, I get actually I fix it by the mass of the row, okay? And then I get here. You see, minus 5.5, this is minus 5. This is perfect. This is, okay, the only one where there is this is 1.6, 1.7, 1.0, 0.85. Really fantastic. Really, 1, 2, 3, 9, and 10, which are those where this vector resonance can contribute. They seems to be saturated by this resonance contribution, whose value, I mean, can be all computed essentially in terms of one free parameter, which is the raw mass. Okay. So that is we want is the power of QCD from the above, who is telling us what this Li have to be. So that is nice. Yeah. 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 So again, I have to decide what I want to do. So, right. So if I want to be agnostic, I don't know anything about QCD except the symmetry, then I measure the Li, okay? And then I can proceed, I can also do my paper scattering all in terms of the Li. Then if I want to understand what the Li are, okay? Suppose I couldn't measure them, then these arguments are good to get a determination of the Li from theory, not from experiment, okay? Again, so this is interesting. Of course, in QCD, you say, who cares? Because I measured the Li, you're right. And then if I use the Li, I don't need to use the resonance, okay? That's either I use the Li or I use the resonance. Yeah, but you see, this is just a trick to get the Li via this matching. So you should think this as a matching procedure. So I have the theory, the theory with the resonances tell me that when Q square is much smaller than then I compute this effect here. So I can see it as a matching condition for my Li. Yeah. Yeah. Well, not in a sense. So I introduce them to compute the value of this term here. Okay, then if I put this and the Li, then I get a double counting.
The mu when is the order of the rho and this other, you have Li intermediate plus rho resonance.
Yeah.
When you put them together, you have Li low energy.
Oh, indeed, yeah. So it's also true that people consider, yeah, you can consider the Li with the vector resonance contribution plus the residual term. That you can also do it. I agree. That's good. Yeah. So you yeah, you can think indeed, maybe indeed, probably the correct way to think of this. So you have this Li which even are generically dependent on mu. So you can see there are these Li resonance which are constant. Okay. Then there is some delta Li which that carries the mu dependence. Okay. Okay. And this is and these are the usual term. Okay. But these are much smaller than that. That is what I'm saying. Okay. Of course, then so there is a dual description. Then otherwise you can go to a description where you just look at this and you ignore the rest of contribution. Then it's everything. Okay, this is big. Yeah. So one has to be careful about the double counting. Yeah. Well, this really need to compute it in perturbation theory. Okay. But for instance, it's tricky because you need perturbation theory and some answers about for the Pioneer wave function. So that's pure perturbation theory. You need that is really pure perturbation theory. Okay, that is why I want to show that example. I mean, it's yeah, yeah, yeah. Why this? Because again, you're QCD now forgetting about the anomalies. Your QCD Lagrangian, it's invariant under the once you add the L, it respect these are neutral currents in QCD. So they are conserved current. So the current Q bar gamma is conserved in QCD up to the anomaly. Okay. Sorry? Yeah. Yes, it's a word identity. Sure. Yeah, this is my declaration. Then of course I measure the mass that seems to fit in the octet. Okay, that is the first thing. except for the small breaking of the phi, which is a bit heavier, but this you understand because there is the strange mass, so not surprisingly there. The transformers octet, they also, the way they, again, historically, the way they couple to pion also respect this octet symmetry, this SU3 symmetry. So this you need to know by experiment, yes.
What is the other term? Because out of 5 only.
Yes, so again, this I now don't remember exactly how it comes, where it comes from, okay? I think probably it comes only from the, so here we get it from the vector form factor. I think there is something just related to the axial form factor, okay? That fix something for FA in terms of F pi. Yeah, exactly. Yeah, so basically, yeah, there are 4 relations which are dictated. Yeah, I think indeed, probably, yeah. One is the vector correlator, one is the axial correlator, then we have this left-right correlator. Once you have these 4 combination of basically current, this is what fixes the behavior. Yeah. Exactly. So it's LL, RR, and LR. Yeah. From LR you get the 2, and from LR you get 1 each. Yes, exactly. Okay, I don't remember this, but you see, all these things were derived even before QCD, simply because it's not even just QCD that you want to have a well-behaved theory at high Q square. All these things are really old, but I think it's worth to. I decided to because are still very important. For instance, we want to build a new theory or a composite Higgs or whatever. So still, this is important. Again, it's a guidance. I mean, EFT is very important. Are very useful, but then maybe somehow having extra constant coming from the UV helps. So this is a bit of an appetizer for next week when you have on the UV part of the lecture, right? Yeah, I cannot. What do you mean prove? No, I don't prove it in a sense. Well, indeed, I don't prove anything. I simply say that it turned out that if I want the vector resonance, so I deduce if you want vector resonance as, so what I basically, the answer is that the lowest line vectors saturate this sum rule. This is the point. So for instance, indeed, also here, when I say, you see here there could have been some other resonance that finally adjusts to get the high Q-square behavior. Well, no, it seems that the adjustment happens as soon as possible with the lowest resonance. And in a sense, it's meaningful because the lowest resonance is the one that here appear with the biggest contribution because it goes like 1 over the mass. So clearly the higher resonance will appear with the suppressed contribution, okay, because of the mass. So you would have a large coupling for that resonance, which doesn't fit. So you need a tuning to not to get it. What? No, I cannot see it, okay? That I cannot see it. No, the sum rule has all the resonances. If you put the data, yes, then you see it. Yeah, so the point is, so the assumption that the sum rule is saturated by the lowest line resonance, this is assumption, okay? So which, however, makes sense in a sense that you want to, would be a fine tuning to do it, because the lowest line resonance are those which is the biggest contribution, are those with the bigger coupling to the pion. Then would be weird not to do it with the lowest resonances. Okay.